last time we have studied that for resonance to occur and for the amplitude to remain high, we need to set up standing waves on a string, right? And we have started discussing about the various cases for standing waves, right? So they are all based on this idea that L will be equal to n lambda by 2, right? So let's start. So the first case is when L is equal to 1 lambda by 2, right? Okay, now here I want all of you to understand what this means is, if these are two endpoints where the string is tied, then we are getting one half of a wavelength between those two, right? One half of a wavelength. I hope you all do understand that this is lambda by 2, because if you think of standard pattern in which we draw a wave, think about it. From one mean position to another mean position here, right? That distance will be lambda by 2. I hope you see that, everyone. Okay? So keep that in mind, right? So when this length of the string L is equal to 1 lambda by 2 or simply lambda by 2, this is the first. Now, like I said here, I'll just repeat it quickly. It's that what happens is the source would start a wave, that wave would go there, it would come back. Now, by the time it's ready to reflect and go back again, the source will produce a second wave. So both the waves will add, and then you will get more amplitude. Then the same thing is repeated the third time, so you should get even more amplitude. But because of damping, we have loss of energy. That's why the amplitude doesn't keep increasing, right? So it will become a high constant value, right? It will definitely be high, right? You will be able to see the string vibrate. Hopefully you remember the video, right? We were easily seeing the string vibrating like this, okay, in standing waves. Okay, so the amplitude becomes high, but it doesn't become infinite, right? Due to damping, and then this process continues, so it maintains a high amplitude. Anyways, so here we have L equal to 1 lambda by 2. So if I will now try to find out what is the frequency, well, here it goes. From here, I can say lambda is equal to 2L, okay, very easy. And then I'm going to use V is equal to F lambda. Okay, I'm going to use V is equal to F lambda. So if V is F lambda, F is V by lambda. Okay, now if we put the value of lambda that we have just obtained here, okay, let me finish it here. So this would give you F is equal to V by, instead of lambda we can write 2L, so V by 2L. Right? So this is the first case or first frequency possible for the standing waves to be set up on the string. I repeat, this is the first case of standing waves possible on this string, right? You see here there is only one loop, you have the minimum number of nodes, that is 2 nodes, and the minimum number of antinodes, that is 1 antinode. Alright? Okay? And this frequency itself is going to be the minimum frequency. It's going to be the smallest frequency possible. Right? So this frequency has a special name. Let me write it. The minimum frequency for which resonance occurs. And we get standing waves or stationary waves. The minimum frequency for which resonance will occur, that's this, and here we also get standing waves again, right? This frequency is called fundamental frequency. It is called fundamental frequency. Okay? that is its name, fundamental frequency. Very, very, very important point. Okay. So what's the formula of fundamental frequency of a string that is tied at both ends? What's the formula of fundamental frequency for a string that is tied at both ends? It is V by 2L. Clear? Okay, fundamental frequency V by 2L. Understood so far? Okay, so here obviously we are getting only one loop. You see, identify the diagram, that way it becomes very easy, right? Just one loop, so L is lambda by 2, from that you can get this easily. Suppose you forget this, no problem, diagram is your friend. Draw diagram, get through it, you are done. Okay, just a few steps, and very simple steps. I hope you are seeing those, right? So that way it's fine even if you cannot remember, but I really suggest that you remember every time you don't want to derive this, right? This is used so often. Alright, fundamental frequency for a string is V by 2L. Okay, right? Now let's go to the second case. Let's go to the second case. Okay. Now the second case would be when L is equal to 2 lambda by 2. Is this clear? Second case would be L equal to 2 lambda by 2. I hope that is clear to everyone. So let's draw a picture for this. By the way, this would just be equal to lambda, right? Or you can picturize it. Here we have got one loop, now we'll get two loops. So this is how it will work. Here will be a node, here will be a node, and here will be a node. Okay? Did you understand the diagram, everyone? Did you understand the diagram or not? Okay. So now here we have two loops, right? Again, L is equal to 2 lambda by 2. Again, this is what I am saying. 2 lambda by 2. So one would be lambda by 2, another loop would be lambda by 2. Okay? So you can see it's the total wavelength like this, isn't it? I hope you are seeing that pattern. So distance between here and here, this is lambda, isn't it? One wavelength. So this whole length is L equal to lambda. Clear? Okay or not okay? Alright. So let's derive this quickly here. So we are just going to do F equal to V by lambda. Okay? V by lambda. And what is lambda here? Lambda is L. Did you understand? Did you understand? We got F equal to V by lambda, but lambda is A. But I am going to write it like this. Okay? I know we can cancel the 2. This is the same thing. I am going to write it like this. 2V by 2L. This was V by 2L. This is 2 times V by 2L. Okay? Is this clear? Right? So that's the second case. This is also a resonant frequency. What I mean to say is, if you are trying to vibrate the string at this frequency, then also standing waves will be there. then also standing waves will be there on this string, right? Okay, but here the situation is slightly different. It's that by the time the wave goes there, reflects and comes back, source would have completed 2 oscillations. I repeat, by the time the wave reaches that end, reflects, comes back, and now it's ready to go back, the source would have completed 2 oscillations. In the first case, we studied that source would have completed 1 oscillation. Here, the source would have completed 2 oscillations, right? Okay, so that is how all this works. So that's how resonance is established. Fine. So this is case number 2. Now, can you draw a diagram first of all for case number 3 on your own? Everyone, I'm giving you 1 minute. Draw a diagram for case number 3 like this on your own. Hurry up. And then you tell me what should be F for case number 3. You tell me what should be F for case number 3. First of all, draw a diagram. Okay, and then you tell me what should be F for case number 3. Hurry up. Not in form of lambda. 2v by 3 lambda is wrong. It cannot be 2v by 3 lambda. Frequency is always v by lambda. Yes, Priyansh is correct. Ankita is correct. Diagram is the key. If you can draw the diagram correctly, nothing can stop you from getting it right. It's very simple after you draw the diagram. Yes, Joy, that's right. Okay, the diagram. First of all, L is equal to 3 lambda by 2. 3 lambda by 2 means 3 times lambda by 2. Such loop 3 times. So you see how I draw it. I don't care what anyone says about this. Okay, done. Did you understand? Okay, you may call it cheating, I don't care. So we have got this here. So now this is lambda by 2, and lambda by 2. Again, distance between 2 consecutive nodes is always lambda by 2. I hope you remember that. So we have L is equal to 3 lambda by 2, so lambda is equal to 2L by 3, obviously. Right? Lambda equal to 2L by 3. So F is equal to V by lambda and V upon lambda. Lambda is 2L and upon 3. So this time it is 3 into V by 2L. I hope you are seeing this pattern. 1V by 2L, 2V by 2L and 3V by 2L. Understood? Yes or no? So in general now, okay, time for the most general relation. Okay, number 4, in general. In general, L is n lambda by 2, therefore lambda is 2L by n. Therefore V is equal to, therefore F is equal to V by lambda, right? Okay, and V upon lambda means upon 2L divided by n. So n will go to the numerator. N will go to the numerator, therefore F is equal to n times V by 2. This is the formula of resonant frequency or natural frequencies of string tied at both ends. I never said it complete 3 oscillations. Can you please clarify who is it or what is it? Wave cannot complete oscillations, Aditya. Wave is not an object. Source completes 3 oscillations. Source will complete 3 oscillations by the time wave reflects and comes back. That's why we will have resonance. Okay, just like you push a child on a swing, then you wait 3 times. 3 times, that is for 3 oscillations. Okay, so imagine it, everyone. You push a child once on a wave, on a swing. Okay, then you wait. Right? Then you wait. The swing will make 3 oscillations. Like you push it, goes there, comes back 1, goes there again, comes back 2, goes there again, comes back 3, and now you push it. Right? So that is the kind of behavior that is going on here. Remember, wave is not going and coming back 3 times. That's not what I am saying. What I am comparing here is that the source, when you push the source, the driving force has to wait. So that's what is going on. The wave will go there and come back, and in that time the source would have generated 3 waves, right? So on the 4th time, the reflected wave and the new wave will match. They will add with each other, amplitude will be more. That's how resonance will occur. Okay. Now, so this is the most general formula here. You should definitely remember it, and you should also be able to draw diagrams for such cases, right? To be very frank, if you cannot remember formula, nobody cares. Can you draw the diagram? That's it. If you draw the diagram, you can always write the formula. It's very simple. Okay. Now, let's go to the next thing. Start with this again. Okay, let me just first write down the definitions. Okay, in case you want to write them down. So harmonic is an integer multiple of fundamental frequency. Harmonic is an integer multiple of fundamental frequency. That's the definition of harmonic. Right? So what that means is, for example, third harmonic, let's say. Third harmonic would mean 3 times fundamental frequency. Did you understand the example? Okay, harmonic absolutely clear, everyone? Alright. Now let me also write the definition of overtone, and then only we will start with that list. Okay? So what is overtone? Overtone means a resonant frequency which is higher than fundamental frequency. Okay? It should be a resonant frequency that is higher than the fundamental frequency. That's the key thing. Higher than fundamental. Okay? Alright. Now, what about examples of overtone? That I'll give you as we make the list. Okay? Now, I'm going to erase these definitions. Everyone, I'm going to erase these definitions. Have you noted these down? Have you noted these down? Alright. Okay. Because I want to make a kind of a table, right? We'll put that whole list as a table here. So, Let's start. So first of all, the first column is resonant frequency, right? Okay, resonant frequency. Harmonic number. Okay, and overtone number. Alright, so let's see. So first of all, resonant frequency number 1. So this is in serial order. So first resonant frequency, the smallest resonant frequency is V by 2L, isn't it? F equal to V by 2L, correct? What is this called? This is also called fundamental frequency, alright? Okay, so this is the first harmonic. Okay, this is the first harmonic, alright? And it's not overtone, dash. It is not an overtone. Why is it not an overtone? Because as the name says, overtone, over that is higher. That's what this word means. So it should be a higher frequency than fundamental frequency. No, this is itself the fundamental, so it's not an overtone. Did you understand? This is not the overtone. Clear? Because it's not higher than the fundamental frequency. Alright, let's go to the second resonant frequency. The second resonant frequency is F equal to 2V by 2L, right? Based on our list. Alright, it is 2V by 2L. Again, I could cancel 2, but I am not cancelling 2. There is no need for me to do that. This makes a very nice pattern. So this is, do you realize, double, 2 times fundamental frequency, yes or no? 2 times fundamental frequency. So we call it second harmonic. Is this understood? So we call it second harmonic. Is this understood or not? Second harmonic. Why second? 2 into fundamental frequency. Look at the bracket. Okay. Then what about overtone? Now see. This is the first resonant frequency, which is the fundamental frequency. Then this is the next resonant frequency, which is obviously higher than that, right? You can see that. This is 1, this is 2 times, so it's higher than this. That's why this is called first overtone. Did you get that? Did you understand why it's called first overtone? First higher frequency for which you get resonance. I repeat. This is the first higher frequency for which you get resonance. Alright? Okay? Then, the third resonant frequency according to our pattern would be 3V by 2L. Correct? Okay? 3V by 2L. Then that would be third harmonic. I hope this is absolutely clear. Right? Because this is 3 times fundamental frequency. Right? And this is called second overtone, not third overtone. Again, why second overtone? Simple idea. Fundamental frequency is the basic or the smallest resonant frequency. Above that 2V by 2L and above that 3V by 2L. Right? So this is the second higher frequency. Right? I hope that makes it clear. This is the second higher frequency. Overtone number has numerical value. What do you mean to ask? We call this frequency, basically these are names. Basically these are names. Okay? So someone says frequency 3V by 2L for a string is which overtone, then you can just answer second or second overtone. Understood? Right? Okay? Alright, and so on so forth. This will continue. I am not going to write many more. Okay, so that's what is harmonics and overtones. Right? Be careful, they are different. And please, nobody will try to mug up that this is 2, then that will be 1, and this is 3, and that will be 2. Okay, that's nonsense. Right? I didn't explain it like that. There would be some reason, don't you think? Otherwise it's very easy to point it out. But I didn't point it out, right? Because if you try to remember it that way, you're going to make trouble for yourself later. Okay? So there is no relation between these two. Remember, there is absolutely no relation between harmonic and overtone. They are irrelevant to each other. They are independent from each other. Okay? So don't try to do it like that. Follow the definitions of harmonic and overtone. Okay? Let's go to the next thing now. Alright, now the next thing is resonant frequencies in an open organ pipe. So this is our first exposure to sound waves, right? Okay, what is an organ pipe? Basically, an organ pipe is just a tube which is hollow throughout and open at both ends. If we say open, I repeat, we are going to talk about resonant frequencies not in a string now. We are going to talk about resonant frequencies for a pipe, okay, with air inside it. Right, and it will be open on both ends. Is that clear? Open on both ends. So let me just clarify it. Open organ pipe is open at both ends. Okay, you might say, sir, what nonsense? This is so simple. Be patient, right? There are so many people that can get confused if you don't write all this. Okay. Right? It is confusing, let me tell you that. Right now you might be thinking open is open, right? Nothing to worry about that, but it's not so simple. Later on there will be confusion. Okay, so open organ pipe is open at both ends. So typically this is what it looks like. Right? Now what will happen? Listen. When someone will blow air or someone will produce some kind of sound at this end, one end, then waves, sound waves will be set up in the air inside it. Did you understand? If you make some sound over here at this end, or even if you blow air, then sound waves are generated everywhere inside this pipe. Alright? Now, you know again that sound is a longitudinal wave in gas. Air is a gas. Right? So it will pass through. It will pass through using a series of expansions and compressions, right? That is expansion and rarefaction. Hopefully you remember that. Okay? So what happens is, just like, listen to this carefully, just like for a string which is tied at both ends, just like for a string which is tied at both ends, there are only some frequencies for which resonance will occur. There are only some frequencies for which resonance will occur. Why are there only some frequencies? Because wavelength and length of that string should follow this relation, correct or not? If this relation is not followed, then standing waves cannot be generated. Basically, only then resonance will occur, right? So based on that, we got a list of frequencies that follows this pattern, right? That's what we have just finished. Alright? So only these frequencies can generate standing waves, others cannot, right? Okay, others cannot. So just like that, over here in this pipe also, all kinds of frequencies of sound do not generate standing waves of sound. I repeat, all kinds of frequencies of sound do not generate standing waves. There are only some frequencies for which resonance will occur and there will be standing waves. Is it clear what I am saying? There are only some frequencies for which resonance occurs and there will be standing waves. Got it? Just like string basically, just like the string. Okay? Right? ગમે તે frequency હોય તો એમાં standing wave no generate થાય. There is a condition. Right? There is a condition for that also. Right? Just like it was in string. Okay. So here what's the condition? So first of all, listen to this carefully. First of all, we must understand the concept of something called pressure node and pressure antinode. Listen to this carefully. There are a few things that we need to understand. You see, without going into too much of the maths, we don't need it at this stage. It's that equation of a transverse wave. We were writing it like this. Let's say it's traveling towards the positive x-axis. Let's say like this. Okay, assuming phi 0 is 0. This is for a transverse wave and this displacement. Right? Similarly, listen to this carefully. For a longitudinal wave like sound in air, what happens is there are alternate regions where there is expansion and where there is compression, right? Okay? I hope you remember that. So what happens is obviously where the pressure is more, the air gets compressed. Did you understand? Where the pressure is more, the air gets compressed. Where the pressure is less, the air expands. Clear or not clear? Clear or not clear? Where pressure is more, air compresses. Where pressure is less, air expands. I'll make the last point again. Okay, I said that when sound passes through air, there are alternate regions of compression and expansion, right? We have talked about this earlier, you have learned it in 9th, I'm not going to go too crazy about it. So what happens is, just like in case of displacement, some particles go up, some particles go down like that, okay, compared to the mean position. In pressure's case also, that is when sound passes, pressure also follows this kind of behavior. Okay, a pressure wave also follows this kind of equation, right? What does this mean? Listen to this carefully. Listen to this carefully. Suppose these are two endpoints of this pipe. Okay, suppose these are two endpoints of the pipe. I am going to draw a graph. I am going to draw a graph of pressure. I am going to draw a graph of pressure versus position. That is x. This is a graph, mind well. Graph. I am repeating it 3 times. It's a graph. Okay, of pressure versus position. So what will happen is there will be a mean pressure. This is something that you need to understand. There will be a mean pressure. Mean pressure, that is the average pressure of air when you don't produce a sound. Right? Let's say there is just air, you are not trying to produce a sound. At that time the air will have some pressure. That is the mean pressure. Right? So now wherever compression will occur, let's say in the first region compression occurs. Why would compression occur? Because pressure is more than the average pressure. So it would be like this. So this is a compression part. So here what has happened is that in these points the pressure has risen compared to the average, it's more. Then after that you are going to get expansion part or rarefaction part. Let's say this is the rarefaction part. So why is there expansion of air or why is there rarefaction of air? Because the pressure is less than the average. Did you understand this? Did you understand the graph? After that, what will happen? The next region will be for compression once again. So like this, here the pressure will be more than average. So that's why delta P is positive. See, what is the meaning of delta P? Delta P simply means P minus P0. Just like here, Y stands for displacement. Do you remember? What is the meaning of displacement? Displacement from mean position. Just like that, delta P stands for change in pressure from mean pressure or from average pressure. Did you understand? Delta P stands for change in pressure from mean pressure. Right? So this graph, do you realize that this graph is just like the graph of Y that we would normally be drawing in a transverse wave on a string? Yes or no? Clear what I have said? The graph of pressure is similar to the graph of displacement that we could draw. Okay? Now what does this mean? It means that when we are talking about sound wave, then instead of talking about displacement and all that, we can just talk about pressure. Okay, I repeat what I have said. Instead of talking about displacement and all that, we can just talk about pressure when we are talking about a sound wave. Alright, so keep that in mind. Now, what is a pressure node and what is a pressure antinode? Right, listen to this carefully. Earlier we have learned that node means where amplitude is 0. Right? Node would mean where amplitude is 0. Okay? Right? Alright, node would mean where amplitude is 0. Now, just like that, a pressure node would mean, listen to this carefully. A pressure node would mean a point where change in pressure is always 0. Did you understand the meaning of pressure node? Did you understand the meaning of pressure node? Pressure node would be that point where the change in pressure is always 0. Okay, I see video doesn't work anymore. See everyone, now it's already time. Okay, I think we should end this class. We will continue with this point the next time. Alright? Okay? Goodbye everyone. I'm going to end the meeting. You'll be ready for your chemistry class at 9.